So I should thank Ravi Shankar also. I wanted to start off by thanking Hassan and Sibashish and Simon for inviting me to give this set of lectures on geometric phases. I thank Shankar also and for introducing me. I have not assumed any prior knowledge of this subject, only basic quantum mechanics. But I am sure some of you or many of you may already be familiar with the subject and may not find much which is new in these lectures. But at least then I hope that there are others who will find this a useful introduction to this subject. So I am going to start from basics. The other thing is I had not expected such a large audience. So I would be grateful if a photograph can be taken now so that I know in the future how many people were here on the first day. It doesn't matter if the number goes down as we go along. So I want to repeat that I will start from the basics. I will assume only the knowledge of the quantum mechanical framework necessary for these lectures. So first let me give you an overview of and the scope of this. Yeah.
You know, long back you gave a course of lectures on group theory.
Here, yeah.
And then towards the end, maybe on the last day or the day before, that was some 17, 18 or 20 lectures. But it's a very large number.
I know the number also, I know the year also.
Yeah, but I don't know.
Yeah.
And towards the end, you narrated this background of this parallel symphony.
Yeah,
it was
true.
very appropriate.
Yeah.
In this course, there may not be any natural setting for you to say that
That's
thing. But
Yeah.
You can say, if you want, you can say that now. It was a very interesting thing. Not interesting. People here.
Oh, that is true. So just to complete what you said, those lectures were given over the months of September to November 2007. And there were a total of 40 or 44 lectures. And this story was about the Western classical composer Haydn, Franz Joseph Haydn, who was employed at a certain time in his life by a very rich count, I don't know, in Austria or Hungary, Count Esterhazy. And the count made Haydn work very, very hard and never gave him any rest. And the orchestra never could take leave at any time. So the only way Haydn was able to convey the message to his employer was to compose a symphony. It is number 100 or 103 or something like that. He composed 105, I think, the largest of any one composer, and it's called the Farewell Symphony. And it is a very beautiful piece of music, but as you go from the first to the second movement, he composed it in such a way that a few of the performers, their roles were over and they could leave. And then after second movement, some more could leave. After third movement, some more. And when the symphony comes to an end, just a handful of the original players were left in the room. So in this way, he was able to convey his message to Count Esterhazy that it is time he gave some break to the musicians. So it's a very famous piece. You can go to the internet, Haydn's Farewell Symphony. It is around 195 or 103 or something like that. So I remember this from my early days. All right, now this, I have just been writing my lecture notes for this series of 5 lectures day after day. It's not yet concluded. I still have to write a few pages on the last topic, but I might just tell you the titles and not spend time writing them on the board. The first, so totally there will be 6 sections when it is done. The first is an overview of the lectures, the scope of the material I want to cover. And by the way, Simon and I and Chaturvedi, many of us have done work in this subject for more than 20 years now. So the way I present it is the way we have understood this subject and the way we have contributed to it. So the first section, which is very brief, will be an overview of the subject. The second section will be a description of Berry's original discovery, but I will present it in two ways. First, a simplified version, next Berry's original way in which it was discovered. The third section will be the generalizations to Berry's work found by Aharonov and Anandan a few years after Berry, and then another year later by Samuel and Bhandari, further generalizations. And in that third section, I will introduce a few preliminary mathematical notions, some geometrical ideas relevant to the structure of quantum mechanics. The fourth section will be basically Simon and my approach to the geometric phase, called the kinematic approach. And in that section, apart from describing this work, I will also bring in the notion of Bargmann invariants and their connection to geometric phases, and a set of interesting applications of the entire formalism. Fifth section is going to be a second mathematical interlude, where some specific features of quantum mechanical state spaces, on the one hand its symplectic structure, on the other hand its Riemannian structure, will both be highlighted. And the last section will be something we have been doing recently and completed about a year ago, called the null phase curve idea. So that is quite new. So let me start now with my first overview section. As all of you, I have not assembled a set of references. They are easily available. If somebody needs them, we can type them up and circulate them later on. So Berry's discovery of 1983-84 was of a new phase in the context of the adiabatic theorem in quantum mechanics. And this work of Berry initiated enormous amount of activity worldwide. In Berry's derivation, several independent assumptions were made. Initially, this phase was called the Berry phase by everybody else, but over time the name has more or less changed to the geometric phase. And as you will see, this concept is relevant also in classical wave optical situations. I am personally very happy to see that now there is a chance of its being used in the condensed matter context. That will be very, very nice. All of us will learn something out of it. On the other hand, I hope the way I present it will help you to make those applications. So as I said, many efforts were devoted to relaxing the assumptions made by Berry to see how to define the geometric phase under more general conditions. The first important step was taken by Aharonov and Anandan in 1987. The second important step by Samuel and Bhandari in 1988. Then Simon and I, our work on this was published in 1993. So these are three successive steps in generalization, which I have picked up and I will describe. At the same time that these generalizations were being explored, people also were looking in the earlier work, earlier literature, to see if there were papers, ideas pointing in this direction much earlier than Berry. There may be several, but the two important ones which I will touch upon as we go along is the work of Pancharatnam in classical polarization optics in the year 1956, which is 27 years before Berry's work. This fact that Pancharatnam had done work in the direction of the geometric phase was pointed out by Ramaseshan and Nityananda in 1986. The other important early work relevant to this subject is the work by Valentine Bargmann in 1964, again almost 20 years before Berry, in discussing Wigner's theorem of 1931, a theorem which Wigner had proved on how symmetry operations can be represented in quantum mechanics. So, that theorem itself is very early in the history of quantum mechanics. It is from 1931. Many people had tried to give alternative proofs of Wigner's theorem over the years. One of those efforts was by Bargmann, which is particularly elegant, and I was familiar with Bargmann's work, 1964. So, the fact that Bargmann's work is an important precursor to the geometric phase was pointed out and exploited by Simon and me in 1993. So, these lectures will describe all of these things and more mathematically relevant structures in a more or less chronological order. I have already given you some idea who did what and when. But I will not be strictly chronological. I will not start with Pancharatnam's work today. I will refer to it at a suitable point. So, you will find that many features of quantum mechanics, which you might already be familiar with, they will be re-examined, they will be refined from this geometric phase point of view. And when I come to the kinematic approach of Simon and myself, I will describe in a little bit of detail some of its applications. So, that gives you an idea of the overview and the scope of these lectures. Now, there are many equations and I have numbered them section wise. So, as far as possible, strength, energy permitting, I will write all the equations on the board with their numbers. If I miss some, we will see how to go about it. And at any time, please intervene with questions, comments, clarifications, etc. So, now I will start my section 2. So, I will begin with Berry's work, but first I will describe what he found in a slightly simplified form compared to his own paper. And we always say Berry's work of 1983-84 because apparently he submitted this work in 1983 and it was of course rejected. What was it, physical review? I don't know where it was sent first. So, I remember Professor Harry Lipkin, a well-known particle physicist from our days, starting a seminar with the words, "I would like to describe a very nice piece of work which is in the process of being rejected by physical review letters." It is like that. So, Berry's first submission to the journal was rejected, but it must have been around in preprint form because before it actually appeared in the Proceedings of the Royal Society in 84, a physical review letter on Berry's work had already appeared, that is Barry Simon's work in 83. So, that is why in these, whenever I talk about it, I always say Berry's discovery of 1983-84. So, now we have some quantum mechanical system in mind. It has pure states and mixed states. We will almost all the lectures deal with the pure states only, and we will denote the corresponding Hilbert space for the quantum mechanical system by the symbol script h. Then we imagine that we have a time dependent Hermitian Hamiltonian operator governing the system, and we have a state vector at each time psi of t. So, the state vector obeys the Schrodinger equation, time dependent equation. So, this is my equation 2.1. Now, if the Hamiltonian had been time independent, formally a general solution of the Schrodinger equation is very easy to construct formally. Because what you do is that you take the Hamiltonian in the time independent case. You take the Hamiltonian and find out all its eigenfunctions and eigenvalues. For simplicity, let us assume everything is discrete. If there is a continuum, we have to change the notation a little bit. So, we solve the eigenvalue problem for the time independent Hamiltonian. We know, because it's Hermitian, that the eigenvalues will all be real. Now, I will use a very flexible notation for scalar products in Hilbert space. Sometimes I will use the bracket symbol, sometimes I will use the Dirac notation, just depending on convenience. So, we know, so these two things mean the same thing. We know that the eigenfunctions for different eigenvalues are mutually orthogonal, and we assume each one of them is normalized. So, for simplicity, we will assume that the spectrum is discrete as well as non-degenerate. Then we also know that this set of eigenfunctions is a complete set. So, we have a complete orthonormal basis on our Hilbert space. So, in principle, the general solution of the Schrodinger equation is very easy. Suppose you give the form of the wave function psi of t at time 0, and you expand it in terms of these eigenfunctions. Then you will have well-defined expansion coefficients, complex numbers, and once they Cn are known, then formally the solution of the Schrodinger equation is just the same expansion coefficients multiplied by time-dependent exponentials times the eigenfunction psi of n. So, given psi at t equal to 0, expand it in this basis of psi n, then insert for each term in the expansion corresponding exponential factor. So, this is very simple, in principle very straightforward. And this is the general solution to the Schrodinger equation. And as you know, well, as I have written, the expansion coefficients are constant in time. The psi n are called the stationary states of the quantum system, and the Ens are the eigenvalues. Now, I have assumed that the eigenfunctions psi n are an orthonormal set, so then each one of them is a unit vector, but it leaves free a phase factor in each psi n. So, each psi n is determined up to a corresponding multiplying phase factor. Okay. Now, let us, so this is well known. Now, let us go back to the more general case where the Hamiltonian has a time dependence. Then what we will do in this case is that at each time we solve the eigenfunction eigenvalue problem for the Hamiltonian at that time. So, we will have generalizing what I had here, the equations I am now writing. And for simplicity, we will assume again a non-degenerate, discrete spectrum of eigenvalues. The only thing is that since as an operator, the Hamiltonian changes from time to time, its eigenvalues can change with respect to time, and its eigenfunctions can also change with respect to time. So as I had written earlier, now I will generalize the statement and say that the eigenvectors at each time form an orthonormal set, and of course also they form a complete set. And as I said, sometimes I will write one kind of notation, sometimes another, bra and ket, or sometimes psi and psi adjoint. So this is in principle available to us at each time. Yeah.
Means that for each time I'm changing the basis.
Yeah, yeah. At each time you have a basis belonging to that time. Correct. Now, in the time-dependent case, the eigenfunctions psi n of t are not called stationary states because they are not stationary. Apart from that, how much arbitrariness is there in the choice of each psi n of t? Each psi n of t is fixed up to a corresponding time-dependent phase. Want to say something?
What is the problem of this? I'm not able to cover it easily. So if you only use that
Ah,
code, I want to divide the code into two. So let it be in 4 halves.
oh, it should not be full length.
I'm not able to cover the code.
Ah, okay, okay. All right, from this point onwards, I will do that. Huh? So each equation should run half the length only. Okay, so is this roughly center? So I will try not to, okay, I'll come to that. All right, and I'm sorry for that. So each psi n of t is known apart from a phase factor which can depend on time and which can also depend on n. So to that extent it is determined. Now of course there is no way to find exact solutions to the Schrödinger equation, even though you might have solved this eigenfunction eigenvalue problem for the Hamiltonian at each time. So what you do is the following. You try, anyway, this is something that you can always do. There are many equations which I will write which are exact in the sense that they are directly consequences of the time-dependent Schrödinger equation. When we make an approximation, I will tell you. So what we do is the following. The unknown is the psi of t obeying equation 2.1. So let us expand it at each time in terms of the eigenfunctions of the Hamiltonian at that time. All right? So make this expansion. Of course, this will reduce to equation 2.2 in the case where there is no time dependence in the Hamiltonian. The C's will become constants. The energy eigenvalues En of t will become time independent. So what I have written there, that integration over the instantaneous eigenvalues will just reduce to this factor, and psi n of t will also be time independent. Now suppose you use this expansion in the Schrödinger equation, in equation 2.1. So now this is going to be a little bit tricky, so I will break it into two lines. That is all I can do. So just take this equation expansion 2.4, use it on the left hand side and on the right hand side, and what is it that I will get? Let me write everything out. This would be what you get on the left hand side, right? Because you have to differentiate first the c, then the exponential, and then psi itself. And what you get on the right hand side, it is much simpler, only a single term. Correct? Because I just get on the right hand side, when you put that expansion in, I will get the eigenvalue En of t dependent on time when the Hamiltonian acts on psi n of t. This means, so one term on the left cancels the term on the right. You can see that this term will cancel this one. So this becomes sum over n Cn dot of t psi n of t Cn of t psi n of t dot e to the minus I by h bar right? Only the first and the third term on the left will survive. So this is equation. So this equation is exactly the same in content as equation 2.1. There is no approximation of any kind. So now we want to break this up into pieces, and the way to do it is, imagine taking the scalar product of this whole expression on the left with a general psi of one of these time-dependent eigenfunctions. So I will take the scalar product of the expression on the left with some psi k of t. So taking the scalar product with psi k of t, let me just indicate it like this on the left. So then you will isolate one term here, and so this equation will become so all I have done is take the scalar product of the left hand side of equation 2.5 with a general element of the basis at time t, orthonormal basis psi k, the kth one. So you can say that this is true for each k. So I might indicate it explicitly. So this equation we have is exact. It is the same as the original time-dependent Schrodinger equation. Nothing has been approximated. And now let us see roughly here. Is that okay? Yeah. All right. Now I want to analyze this factor, the inner product between one of the eigenfunctions at time t with the time derivative of another eigenfunction, psi k with psi n dot at an arbitrary time. And that is quite elementary, but I will go through the steps. You start with the energy eigenvalue eigenfunction equation. It's the same thing as I had up here. And you differentiate both sides with respect to time. So you will get two terms on the left and two terms on the right. So I will have right? You get two terms on each side. And now what I do is take the scalar product with some psi k, as I did in the previous manipulation. So when I do that, on the left I will get this is the first term, right? Psi k in the first factor in the scalar product, operator dh by dt, psi n. And then the second term, when I take the scalar product here with psi k on the left, remember h is Hermitian, so I can make it act on psi k on its left. So the second term will just become, second term on the left will become this. I hope you see this immediately. And on the right, you have the same two pieces as before, except that we have taken the scalar product with psi k. So this will give me a Kronecker delta in k and n, and I get that. You can see it is appropriate to combine this term and this one. It will produce an energy difference. And so by moving this term to the right and this one to the left, I get the final form of this equation. Let me write it. So this is the result of taking the time-dependent Schrodinger equation, putting that expansion at each time into it, and then taking the general scalar product with psi k of t in that same basis. So this is also an exact equation. Okay, there is no approximation involved in getting this result. And this is true for every k and for every n enumerating the eigenvalues and eigenfunctions of the Hamiltonian. Now, for the case k equal to n, you get one kind of consequence from this equation. For k not equal to n, you get a different consequence. What happens when k equals n? This energy difference becomes 0, the left-hand side becomes 0, the Kronecker delta becomes 1, and so you get an expression for the time dependence of the eigenvalues. This is a useful thing to know, quite elementary. It's a consequence of the time-dependent Schrodinger equation. Okay, all right. Next, you look at the terms where the index k is different from the index n, and remember we are assuming non-degenerate spectrum all the time. So in that case, this energy difference is now non-zero. En is not equal to Ek, so you can divide through and you get a result for the thing that we were looking for. What is this expression? This is what we needed in this last term here. So we have managed to isolate it. So this is equal to, again from here, just a little bit of algebra. Later on we will have more interesting things to say, but just bear with me for this derivation. All right, so we have found an expression involving the instantaneous energy differences, the explicit time dependence of the Hamiltonian. In terms of those things, we have an expression for the inner product between one of the eigenfunctions at a time t and time derivative of any other eigenfunction. So k not equal to n. So this is important to use in that Schrodinger equation. So what we have not been able to determine in any simple direct way is the expression for the case when k equal to n. What can we say about this? We know that each of these time-dependent eigenvectors, eigenfunctions, is arbitrary up to a phase factor which may depend on n and which can depend on time. That freedom we have with us all along. So what we do is that we agree to restrict the degree of this freedom in the phase of each psi n as a function of time, so that for k equal to n, this is 0. Okay? So we will make this a convention, or we agree to do this. So now you can see from this condition that each of these time-dependent eigenfunctions of the Hamiltonian, if it is given, if it chosen in some way at t equal to 0, For later time, there is no remaining flexibility. The phase freedom in the choice of psi n of t at each t is eliminated by making this requirement. So let me repeat. 2.9 is a straightforward derivation of the basic equations, the eigenfunction, eigenvalue equations, etc. This one is a convention. We do it for definiteness and for convenience. Then we can make use of these results in the equation 2.6, which was what? Exactly the content of the time-dependent Schrodinger equation. So what we do is we put this into that, and then I will write it. I think it will fit in this board. It will take 2-3 lines. So let me stress that what I am writing is an exact consequence of the Schrodinger equation. In this summation over n on the right, the term n equal to k will not appear because we have made a convention. What was that? Equation 2.10. So the only terms that remain on the right hand side are for n different from k. So I have mentioned it here, and it will be Cn of t. The rest is exactly what I have on the equation there. I simplify things a little bit by introducing frequency differences. I will define them in a moment. Only the terms n not equal to k remain, and for this I've just computed what it is. So I will write it in terms of that. So this is summation over n Cn of t over h bar omega k n of t e to the I This is true for all k, and this quantity omega is omega k n of t is the energy difference between the level k and the level n at time t divided by Planck's constant. All right. So I want to,
Every time t that
yeah, we make that a rule by which we limit the freedom in the choice of phase of psi n of t. So it is imposed at all time. Okay. So once you have imposed 210, once you know as vectors in Hilbert space all of the psi n at t equal to 0, then you know them for all time. Just have to be evolved along with the Hamiltonian. Okay, so the freedom is taken care of. So now I want to stress that this is again exact. Up to equation 211, it is just the original Schrodinger equation manipulated, paying attention to the fact that we are allowing the Hamiltonian to vary from time to time. Okay. Okay. Now we go to the adiabatic situation. This theorem, the adiabatic theorem of quantum mechanics, was originally proved by Max Born and Fock in the year 1928. So we make the assumption that our Hamiltonian, which has a time dependence, is a slowly varying operator. That is to say that in some physically reasonable sense, the partial derivative of the Hamiltonian with respect to time is a small operator. It is in the spirit of ordinary time-independent stationary state perturbation theory, where you imagine you have a Hamiltonian h0 and you add a small piece to it, and you say we will assume the added piece is small relative to the original Hamiltonian. So here, this is the adiabatic condition. It is that dH by dt as an operator is small in a suitable sense. So let me just say this is the statement or the assumption that this is small. Exactly what we mean by small will become quantitatively clear in a moment. So then we can say, physically it is reasonable to say that psi n of t, the instantaneous eigenfunctions of the Hamiltonian, instantaneous eigenvalues, and also the expansion coefficients Cn of t in the solution to the Schrodinger equation, it is reasonable to say we expect them also to be slowly varying quantities. Because the Hamiltonian is changing slowly, this will also change slowly. See that in the limit, when h becomes constant, time independent, none of these have any time dependence. So it is a reasonable physical assumption. So now, suppose, now this goes back to the original Born and Fock derivation of the adiabatic theorem in quantum mechanics. Suppose you start with, you try to solve the time-dependent Schrodinger equation with the following initial condition. You say that at, let us say, t equal to 0, psi of 0 is equal to a particular one of the eigenfunctions of Hamiltonian at time 0. So this means that in the expansion of the psi of t in terms of the instantaneous eigenfunctions, at t equal to 0, you assume that it is the nth eigenfunction of the Hamiltonian at time 0. What I will now do is use this input in this right-hand side, where, remember, this is an exact consequence of the Schrodinger equation, but now I will make approximations. What we will argue, in order to get an idea of the order of magnitudes involved, because on the right-hand side, in the spirit of first-order perturbation theory, because this dH by dt has appeared explicitly on the right, the so-called small quantity is explicitly there, to get an idea of the magnitude of things, in all other expressions, symbols on the right, we can neglect the time dependence. This is in the spirit of first-order perturbation theory. So what we will do is, on the right, remember, I repeat, this is an exact equation. But now, because we have assumed this factor is a small quantity, because it is there explicitly, then to the first order of smallness, everything else can be treated as it would have been in the time-independent case. And then what does this become? you can see that with this understanding of what we mean by small, we get the following approximate results. And this is the first time when we have non-exact statements. For k not equal to n, now please remember n is a chosen one of the eigenfunctions of h at time 0. So I'm setting it apart. So n has a privileged meaning from this point onwards. So for k not equal to n, from here you can see that you will get only one term, because for everything else, for the Cn of t, omega kn of t, En of t, psi of t, you are putting in the time independent values to first order in perturbation in the small quantity approximation. And then you will say the expansion coefficient for the nth initial eigenstate, that remains approximately 1. It starts as 1 and it remains close to 1. And this can be immediately integrated, and it has the following form. So for the first time, I am putting approximate equality signs. It is in the sense of the adiabatic hypothesis, the dH by dt being a small quantity. So you can see that while the expansion coefficient Cn of t remains close to 1, all other expansion coefficients, of course, they start with the value 0 at t equal to 0. At later times, none of them grows in a significant way. They are all just oscillatory quantities. This is just a function which is bounded by 2 in magnitude at best. So you can say that if yeah, it is already first order of smallness. Okay, that is understood. Yeah, you're right. So provided one condition is satisfied, namely this part times this part remains small, that is so provided this, if the following condition is satisfied, if this condition is satisfied for all time, of course, that we are interested in, for all non-diagonal terms, that is for k not equal to n, then here is the expression for the approximate solution to the time-dependent Schrödinger equation. So this is the statement of the adiabatic theorem of quantum mechanics, as originally proved by Born and Fock, 1928. So here is the quantitative statement about what we mean by the adiabatic condition. So this is something that must be satisfied for all k different from n. So what is the right hand side? It's the energy difference between level state n and state k. H bar is there. Here is the partial derivative of the Hamiltonian with respect to time. 1 by omega kn has the dimensions of a time related to, you can say, a transition from state n to state k in suitable sense. So the left hand side, you can see, is dimensionally an energy type quantity, because you have d by dt and you have 1 by frequency. So these two cancel each other in terms of dimension. So the left hand side is of the nature of an energy, and it has to be much smaller than the difference in energy between state n and state k. If this is satisfied for all k not equal to n, then here is an approximate solution to the time dependent Schrodinger equation. This is the quantum mechanical adiabatic theorem. So what it says is that if at time 0 you assume, I think this should not be up in the exponent. It looks like that, no? I better write it properly. Yeah, the equation also is not in the exponent. So it says that provided this condition is obeyed, if at time 0 you start with the nth eigenvector of the Hamiltonian at time 0, if there are no degeneracies all through the time span you are interested in, and no crossing of levels. That is very important, as you can go through the derivation and you will convince yourself. Then at all later times, the solution to the Schrodinger equation is always that nth eigenfunction, instantaneous eigenfunction, time dependent eigenfunction of h at time t, apart from this factor, which is just the time integral of the energy eigenvalue as a function of time. This generalizes what you had in the time independent case, e to the minus I by h bar e times t. So it becomes an integral. So far it is old. It is what it is there in all old textbooks of quantum mechanics, the original adiabatic theorem. Now comes the step taken by Berry, very clever, very imaginative step. So no questions up to this point. I continue. Some of these expressions can go now. Now here is the idea introduced by Berry in 1983-84. Remember, what I am describing now is a simplified form of his derivation. I will give a detailed derivation in the way he gave it because it is useful in practical applications. So I am going to do that as well in a little while. But let me complete this now. Suppose H as an operator, Hermitian operator, suppose it is cyclic. This is the condition, the property introduced by Berry. Suppose there is a time capital T such that the Hamiltonian as an operator at time capital T coincides with the Hamiltonian at the initial time. Suppose this is true. This is called the cyclic condition on the Hamiltonian. Then he asks the following question: what can you say about these approximate solutions to the time dependent Schrodinger equation? Remember, we have the non-degeneracy assumption, we have the non-crossing. Eigenvalues do not accidentally cross in the time from 0 to capital T. We make that assumption. So we have, for each initial eigenfunction of the Hamiltonian at time 0, an approximate solution to the time-dependent Schrödinger equation. The question is, if the Hamiltonian has this cyclic property, what can you say about these approximate solutions? Are they also cyclic in a similar sense? So now, assuming non-degeneracy, something is beeping. It's not this one. Oh yeah, it is. But I put it on silent and I will not answer it. So if this is true, you can see the following. Because of non-degeneracy and no crossing of levels, the eigenvalues of h of t are the same as the eigenvalues of h of 0 because they are the same as operators. And yeah, and then you look at that solution, approximate solution given by the adiabatic theorem. If you started with this as your initial psi of 0, the nth eigenfunction of h of 0, here is the solution given to you by the adiabatic theorem. Of course, approximate solution. And the question we are asking is this also a cyclic quantity? So solution to the Schrödinger equation, it's an approximate solution because we have made the adiabatic condition. Does it share this kind of cyclicity which you have imposed on the Hamiltonian? The answer is yes, because we have assumed no degeneracy at all times and we have assumed no crossing of levels at intermediate times. But we can only say psi at capital T will be the same as psi at t equal to 0 apart from a phase. And why this is so, we will see in a moment. It is very simple. The answer is yes. If the Hamiltonian is cyclic in this sense, what we will find is the solutions given by the adiabatic theorem will also be cyclic, but in this sense. This is the geometric phase. You should call it the Berry phase because this is the context in which he discovered it. And there is one such Berry phase for each value of n. Okay, so you have seen the geometric phase. So I want to write a set of equations which covers all the ingredients. What you find, and I will introduce suitable notation. So these are all approximate in the sense of the adiabatic theorem, but I'll just put equality signs. So here is the full set of equations in your hand. The nth adiabatic solution will be an n-dependent geometric phase times psi n of 0. And what is this geometric phase? We can extract it as follows. I'm writing all the interrelated equations. I'm introducing some notation as I go along. So this is a statement I am making. Remember that old condition which one of you, Bala, asked about. The condition I imposed earlier on, that the phases of the psi instantaneous eigenfunctions shall be adjusted so that this is true at all time. From here, you can work your way back and see that because the Hamiltonian is cyclic, the nth eigenfunction at time t must be something times the nth eigenfunction at time 0, because there are no crossings and no degeneracy throughout. So there must be some phase connecting them. It comes from that equation. It is the geometric phase. And let me write all the pieces together. Here I am dealing with, so actually this is an exact equation. Maybe I can write approximate equality sign where it is a consequence of the adiabatic theorem. So the cyclicity of the Hamiltonian translates into the cyclicity of the solutions of the Schrödinger equation in the adiabatic limit. So the phase which comes there is called a total phase. That's a definition of the quantity phi total. And what is the relationship between these various things? This is something which I want you to convince yourself is true. So these are all statements, symbols which are introduced at this point. There is something called a total phase, and there is something called a dynamical phase, and there is something called a geometric phase. So there are three interrelated quantities, all of them having the meaning of phases. So this is equation 219. So this relation between the nth eigenfunction at time 0 and the time capital T comes out because we have the cyclic condition on H as an operator, and we have put a condition on the way in which the phase of psi of t evolves, psi n of t evolves at each time. So it will lead to some such expression. We combine that information with the approximate solution from the adiabatic theorem, and then you get all these other relationships. There is a thing called the dynamical phase. It is the expression which has been appearing all over the place. This is the dynamical phase. You have to be careful of the sign conventions involved. So time integral of the time dependent energy eigenvalue apart from -1 by h bar is the dynamical phase. The total phase is what relates psi of 0 to psi of t. It displays the cyclic property of the solutions, the results of the adiabatic theorem. That is psi of total, phi dynamical, and the difference is the geometric phase. Okay. So this is an account of Berry's original discovery of the geometric phase, presented in a language a little different from his language. Yeah. Yeah. Which first equation? This one? This one? Yeah?
Shouldn't it be phi total?
No, this is a definition of the geometric phase. Phi total by definition is given here. It is something we define using the result of the adiabatic theorem. Okay. This is the meaning of saying if the Hamiltonian is cyclic as an operator, if there are no degeneracies and no level crossings, then every solution, approximate solution to the Schrödinger equation given by the adiabatic theorem will also be cyclic. And this is the sense in which it will be cyclic. And it's an approximate equation because you have used the adiabatic theorem. So this defines the meaning of being cyclic for solutions to the Schrödinger equation. This is a different thing. This is something which tells you how the phase of every one of the eigenfunctions of the Hamiltonian develops in time because you have made this condition. This is a convention. Remember, where did this come from? We had an expression for psi k of t, psi n dot of t for k not equal to n. We got an explicit expression with energy denominators and so on. Psi n with psi n dot, it is completely uncontrollable because you have initially freedom to alter the phase of each psi n as you like with time. So we made this a convention, a choice of convenience. Once you make this, a relationship like this has to exist. With that, you must convince yourself. And this is the geometric phase. The phi total comes when you discuss the solutions to the Schrodinger equation given by the adiabatic theorem. And now you put all the pieces together. And then this is a full set of relations you get.
I said it's not clear that the geometric phase is convenient anywhere.
Which
Would I not have fixed some different gauge?
Sure. Then, of course, this expression will change. But you will find that when all the dust settles, the geometric phase is independent of all phase conventions. It will come out as we go along. It's one of the important properties of the geometric phase. Okay? It is this fellow which can change. It is a dynamical phase which can change depending on phase choices. The difference, phi geometric, is independent of all these choices. This will be something which you will appreciate as we go further. But now I just wanted to to show you what is the context in which the result of Berry was first found. But as I said, I have given a derivation slightly different from what Berry gave. For the sake of clarity, I have not used the language, the framework which he had introduced. But I now want to give you an idea of Berry's original derivation, which used something called the parameter space. And I like to do it because in practical applications, it is very handy. Now, I don't know up to what time I should go on. I have not covered as much as I had wanted to, but that is understandable. Maybe.
As long as you have letters.
Okay.
Well, I think our lunch
Yeah.
starts at 1 o'clock.
But
I mean,
goes
even
up.
if you
Yeah.
exist a few minutes beyond what is your problem.
Okay. As you can see, my energy is also time dependent, right? So now I want you to pay careful attention to this part. I want to give you an idea of the way in which Berry originally derived it. So the key thing is something called parameter space. Okay. The basic idea in the original paper of Berry is the following. He imagined that you have a quantum system, let us say placed in some classical external environment. Typically it can be a magnetic field, could even be an electric field, I suppose. And that external field is described by some field strength, some parameters. So his treatment was to say, suppose you have a quantum system whose Hamiltonian operator, apart from being Hermitian, depends on some set of real external parameters. So I denote it with a bar below. It's a multi-dimensional thing, real external parameters. So this idea of the parameter space is very important in Berry's original derivation. And then he imagined, suppose the external classical environment is slowly altered as a function of time. It is like putting a spin half electron with a magnetic moment in an external classical magnetic field and slowly changing the magnetic field. That is the physical idea. So what he suggested is that imagine the real external parameters become slowly time dependent. In turn, it will make the Hamiltonian explicitly time dependent because of the time dependence of the parameters. So the framework is like this. To begin with, you denote by R with a bar below a point in a multi-dimensional real parameter space. You imagine that this set of parameters becomes gently time dependent. This will mean that the Hamiltonian for the quantum system becomes explicitly time dependent. So you can say this is a physical way in which the time dependent Hamiltonian, which I have been using up to now, is supposed to arise. So it's a very useful physical picture, and we will see how it can be used. But this is the way in which he posed the problem and solved the problem. So assume that this set of parameters varies adiabatically. What does that mean? Now these are not operators, they are classical real variables, independent parameters. dr by dt should be a small quantity. And now I will draw a diagram for you, and then things will become a little bit more easy to visualize. This is a multi-dimensional parameter space. But for visualization, I can only draw it like this. So let me just indicate what is going on. You imagine that I would mark one more point here. You imagine that the parameters describe some loop, some curve in the parameter space. It's a multi-dimensional parameter space, and you imagine that this is a closed loop. So I will define it explicitly. This curve C is the curve traced by the set of parameters and the condition that it is a closed loop is the set of parameters at time capital T must be equal to their values at time t equal to 0. So you can say he has broken up the cyclic condition in the Hamiltonian as a time dependent operator into two parts. Of course, his whole treatment is starting from that picture. In the simplified derivation, I gave this cyclic condition explicitly in this simplified form, so that you can, I want you to appreciate the idea of the geometric phase, its properties, which we will analyze in great detail as we go along, is not at all dependent on there being a parameter space, on the Hamiltonian becoming gently time dependent through its dependence on parameters. All that is not essential to see the emergence of the geometric phase. So that's why I gave what I call the simplified derivation first. But because his original picture is physically very appealing, I want you to see that also. All right. So here is the picture. Hamiltonian depends on where you are in the parameter space. This parameter space is purely classical. There is nothing quantum about it. It is like external classical electromagnetic fields in which the quantum system is embedded. And this closed loop is a loop in the parameter space. All right. So now to some extent you will see the equations I am going to write now mimic what we gave in the direct derivation. This was based on the original language of Born and Fock. If you look at the derivation of the quantum adiabatic theorem, it is given essentially in the form I have discussed. If you look at Schiff's book, for example, no parameters are involved in that discussion. But now I am trying to present Berry's original derivation in that spirit. So what is assumed is that you have this multidimensional parameter space and you are interested in some portion of it. You are interested in points capital R within some region of the parameter space. So that is the domain of interest. And then for each point in the parameter space, you have a corresponding Hermitian Hamiltonian. So he says, imagine that you have solved the eigenvalue and eigenfunction problem for each set of parameters. So suppose you have solved this eigenfunction eigenvalue problem. So here are the real eigenvalues of the Hamiltonian at some point in the parameter space. You can see that the parameter space is replacing time of the earlier treatment. But I urge you, especially students, to please go through the steps in detail so that you understand the machinery. For each choice of parameter, point in the parameter space, your eigenfunctions of the Hamiltonian at that point will be mutually orthogonal. They'll form a complete basis. So instead of having a basis at each time, you have a basis for the Hilbert space at each point of a multidimensional parameter space. Okay? So what is the freedom in the choices of these? I should not call them instantaneous eigenfunctions and eigenvalues. I should call them the eigenfunctions and eigenvalues at each point of parameter space. Take the Hamiltonian as an operator determined by the point capital R, find out its eigenvectors and eigenvalues. We will assume, let us say, that there is some region in the parameter space inside which we will work. We will not allow the R to go outside of some given region. And we will assume throughout the region of interest, these eigenfunctions are non-degenerate and no crossing of levels. The assumptions we made with respect to time earlier are now made with respect to parameter space. So this means that each of these eigenvectors is determined up to a phase factor, right? They are normalized to unit length, but it leaves free a phase factor in each of them. That phase factor can depend on the parameter values and it can depend on the integer n. The first level or the second level, so on and so forth. So here is an assumption which is made. Within the domain of interest for you in the parameter space, you assume these eigenfunctions are well defined all over as functions of R. no ambiguity, no uncertainty in how to choose these eigenfunctions. So in particular, suppose you started your parameters at this point in parameter space, you have a certain set of eigenfunctions, n for r of 0. And you imagine slowly carrying the parameters like this and coming back. So r at capital T is the same point in the parameter space. The assumption is n for r of capital T is the same as n for r of 0, because r of t is r of 0. And we assume that in the domain in which you are working, these are single-valued, well-defined eigenfunctions of the Hamiltonian, except that each one is arbitrary up to a phase factor. That phase factor is assumed to be single-valued as a function of the parameter r. Okay. So now, having introduced the parameter space, let me see how far I can go. At this point, what Berry does is to appeal to the result of the quantum adiabatic theorem. After all, he's not going to repeat the derivation of the adiabatic theorem, he's going to use it. So what is the Schrodinger equation now for us? Time-dependent Schrodinger equation. It is in his physical picture, you can say. This is the exact time-dependent Schrodinger equation, and it just says, by the adiabatic theorem, if you choose psi at time 0 to be eigenstate number n of H for the parameters r of 0, and there are no degeneracies and no level crossings in the entire region of parameter space, he just says the adiabatic theorem tells us that for intermediate times, the solution to the Schrodinger equation must necessarily be of the kind I am now writing down. So this is the form of the solution to the time-dependent Schrodinger equation, given the adiabatic hypothesis that the nth eigenstate for h of r of 0 evolves into the nth eigenstate for h of r of t as you go along this curve. And of course, it is clear by definition that this phase gamma n starts out being 0 because it has to match with this initial condition. What we will find, we'll do it very soon, is that this gamma of t is not integrable. What does that mean? It is not a function of r of t which could then be absorbed into the definition of n r of t. It is something that survives at the end of a closed circuit. That is the main point. So what we do is this equation. So let me repeat. This is the time-dependent Schrodinger equation where the adiabatic nature of the Hamiltonian is produced by its dependence on some external parameters. The parameters are moving slowly in the parameter space, and this is the result of the Born and Fock theorem of 1928, that nth eigenstate at parameters r of 0 evolve into nth eigenstate parameters at time t apart from the dynamical phase and some other phase which has to be carefully traced. So actually what I will do is I will stop here. It is 1 o'clock. What I have to do is to take this expression, approximate solution to the Schrodinger equation, plug it into the Schrodinger equation, get an equation which tells you how gamma n evolves. And then one has to study that. But there we will see that gamma n, it starts being 0 here. You go along this loop in parameter space, come back, and gamma is not 0 anymore. So it is not something which depends only on r of t and which could have been, attached to n of r. So that is what we have to show. So this is a convenient place to stop. I have to insert this form for the solution given by the adiabatic theorem into the Schrodinger equation, get the consequence for this phase. So you can see that by starting with this expression, we have no summation over complete set of eigenfunctions or anything of that kind. We have used up the adiabatic theorem. State number n at the start of the cycle of this loop C, it remains state number n because there are no level crossings, no degeneracies. So I stop here. If you have any questions, you please ask, but this is a point from which I will resume.